Okay, welcome to the class manufacturing process lecture 3. In the last class we have studied the basics of casting, how casting works, and the various component of a sand mold, and how we can produce casting parts using or manufacture casting parts using sand molding method. And it was the fundamental of casting in the last class, and today we are going to talk about pattern, core, molding sand, and shell molding. Shell molding is one of the casting processes. We'll uh, study that, and also in the case of pattern, we have already studied the classification of the pattern. There are two types of patterns. One is removable, and another one is reusable. So, sorry, removable and disposable. Removable pattern is also called reusable pattern. And in addition, with the pattern, in addition, today we are going to study about pattern allowance. How should we prepare a pattern for to manufacture a certain product? And in the second stage, we are going to talk about core, its classification, its advantages, disadvantages, and also how the cores, what are the properties a core should have to function properly, and also the molding sand, the classification, the constituent materials of the molding sand, and the various testing, what sort of testing we need for the molding sand to be used in the sand casting. And finally, we are going to talk about the shell molding. This is one of the special type of molding process to manufacture products. This is actually the shell casting. You can also say shell casting. Okay, so first is the pattern allowance. What is pattern allowance? To know that, for example, if you have you need to prepare a a part by casting the metallic part, let's say a steel part of this dimension. Let's say length is 10 millimeter, 10 millimeter, with height is 5 millimeter, and then the thickness maybe 5 or 10 millimeter. So the definition of casting says that you need to have a replica of the product to be made. Okay, it is not the exact replica. It actually resembles the shape of the casting and also dimensions, but not exactly the same. The pattern dimension is not the same as the dimension of the final product. Okay. For the pattern, this is the casting you want to make: 10 millimeter length, 5 millimeter width, and then thickness is, let's say, 10 millimeter or 2 millimeter. And to manufacture a cast product like this, you need to have a pattern. Okay, and for that, to make the pattern, if you make the pattern of the same dimension, okay, the dimension of the final product is 10.5, and you are also making a pattern with dimension with the same dimension, then what would be the problem? Can anybody guess? Nobody? Okay, so if we make the pattern the same dimension as the final product, then the problem is that when metal shrinks, when the temperature of the metal, we pour the molten metal into the cavity to produce the product. If we pour the molten metal into this size cavity, and then final product dimension will be less than that. Okay, and to compensate that, we need to make the patterns larger compared to this. A little bit larger pattern should be made, or larger cavity should be made, so that after the shrinkage or after reduction of the volume, it comes to the final dimension what we need for the final product. Okay, and the amount of dimension, that the increased dimension, this must dimension has to be increased in all the side, and in that case this thing is called actually the pattern allowance. That means pattern has to be larger than the final product you are expecting from the casting. Okay, did you understand this far? Are you there, anyone?
Yes, sir, I am here.
Yes, sir.
Yes, sir, I am here.
So you must respond, otherwise it's not possible to take classes online. In the physical class it is possible by looking at you, but I'm not looking at you. So if you don't respond, then there's nobody in there and the class will not be interactive. Okay, if you don't understand, just tell me that I don't understand. But if you understand, then at least response like yes sir. Okay.
Yes, sir.
So the pattern allowance, the definition of the pattern allowance is that the amount of increase in dimension of the pattern compared to the final product that we want to manufacture is called the pattern allowance. And the basic thing in here is that uh, the allowances that we need to provide uh, during the manufacturing of the pattern with the increase or decrease of dimension is called the pattern allowance. Okay, that means the final the pattern dimension is not the same as the final product dimension. The pattern dimension is higher than uh, larger than the actual product dimension. And there are several types of pattern allowances. First is shrinkage allowance, draft, finishing, distortion, and shaking. These are the five basic type of allowances. There could be more. Okay, but these are the five basic types of uh, allowances that you need to really take care of um, manufacture a product with greater precision and accuracy. And to describe the first one, the shrinkage allowance, that means the metal shrinks. The basic thing is that when metal cools, it shrinks in size. It can be either from the high temperature to the melting point temperature. There are three elements actually. This contraction of the volume occurs, comprises of three elements. That means the contraction occurs in three stages. In the first stage, it is called the contraction of the liquid from pouring temperature to freezing temperature. As we discussed in the first class, that the pouring temperature of the molten metal should be higher than the freezing point temperature of that metal, because if you pour the molten metal into the cavity at the freezing point temperature, then you will not be able to obtain a proper casting because material will solidify immediately. Okay, that is why we need to increase the temperature of molten material higher than the freezing point temperature. Okay, the freezing point temperature will be less than the pouring temperature. So pouring temperature will be definitely high. Now when the material is in the pouring temperature, it's if its volume is V1, then at the when material cools down inside the cavity to the freezing point temperature, then and that volume is V2, then which one will be larger?
Sir, B1.
Yes, the V1 volume will be larger than V2. Then there is a contraction. Why this contraction occurs? It's because when the material is at pouring temperature, the atoms have a huge amount of energy, and the vibration of the atoms is higher, and the space between the atoms also increases due to high temperature. And because of that increase in the kinetic energy of the atoms, the volume expands. And when the temperature decreases, that kinetic energy of the atoms decreases, and that is why the intermolecular distance or interatomic distance decreases, and that's why the volume reduction occurs. That means the volume at the pouring temperature will be larger than the volume at the freezing temperature. So one of the contraction occurs in here. Okay, this is the first stage of the contraction. That means reduction of volume. So in the second stage of contraction occurs on the account of change from liquid to solid. That means the phase change occurs from freezing point temperature to the freezing point temperature. Am I right? From freezing point temperature to freezing point temperature. As we know, when the phase changes occurs from liquid to solid, the temperature remains constant. That's why I'm saying that from freezing point temperature to the freezing point temperature. That means in this case, only liquid is transformed to solid. And what happens is that the latent heat is getting released from the liquid to produce solid. And in this case also there is a contraction when the liquid changes its phase to the solid, then again another contraction occurs, and that is also the reduction of volume. Okay, so this is the second stage of the contraction, and the third stage is that the solid at freezing point temperature. Now the solid is at freezing point temperature. When the temperature decreases again, then solid comes to the room temperature or surrounding temperature. So this contraction is due to the temperature drop from freezing point temperature to the surrounding temperature or room temperature. So to summarize these three elements. First contraction occurs from pouring temperature, the temperature at which we pour the molten material into the cavity, that is the pouring temperature. And then the first contraction is from pouring temperature to the freezing temperature, that means the solidification temperature. Second contraction is from freezing point temperature to the freezing point temperature, but the phase is changing from liquid to solid. And the third contraction, freezing point temperature to the room temperature, and this contraction occurs in the solid state. Okay. So for first two contractions, first one from pouring temperature to freezing point temperature, we can get extra material supply from the riser or pouring basin. Okay, we can compensate this contraction. Okay, but in the second contraction, this one can also be compensated from liquid to solid state. Okay, and the final one is the freezing temperature to surrounding. That means when once the solid is formed, then you cannot supply additional material into the cavity, and in that case you need to make the cavity larger, so that after contraction due to the freezing temperature to the surrounding, the material gets its actual dimension. Okay, any question here? And for your information, if you don't feel comfortable asking question in English, that's okay, you can ask in Bangla. All right, so
Okay, sir.
don't hesitate.
Sir. Okay, sir.
So to visualize it, how the pattern allowance works. Okay, the first is that this is the pattern size. We have pattern of this dimension. Okay, we need to make the pattern of this dimension. Then what would be the size of the final casting? This is in the idealized case. If you have a cavity and you don't have any runner, riser, or anything else. Okay, you don't have runner riser, you just have a cavity, and if you filled up the cavity with the molten material at high temperature, higher than the freezing point temperature, then the pattern size, if the pattern size is that, pattern size is indicated as A, then at the first stage of contraction, first shrinkage occurs due to the reduction of volume from pouring temperature to freezing point temperature. There will be a certain amount of contraction which is shown here. And in the second stage of contraction, that means freezing point temperature to the solidification temperature, that means the material becomes solid and hot casting Okay, this is the size of the hot casting. That means this is the second stage of contraction occurs. Okay, and after that, when the material cools down from the solid freezing point temperature to the room temperature, then this will be the final size of the casting. So if you want to make a casting of the B size, then you need to make a pattern of size A. Okay, and the total allowance for the shrinkage is the whole, this is the total allowance or total shrinkage allowance in this case. But when you use the runner riser system, in that case you have to you can ignore the first two contractions. Okay, first stress shrinkage and second stress shrinkage, you can ignore them, but you have to really consider the contraction from solid to the liquid, so sorry, solid to the freezing point temperature solid to the room temperature solid. Okay, any question here?
No, sir.
All right, so the next one is the draft allowance. That is the end of the shrinkage allowance. Okay, so for the shrinkage allowance, to summarize this, is that it is the reduction of volume of the molten material due to the decrease in temperature. Uh, okay, and if you are using pouring basin or pouring sprue and also the riser, then you can ignore the first two contraction, but the third construction you have to consider. But if there is no such option for pouring basin or the riser, then you have to consider all three construction. That means total shrinkage allowance. That means if you want to make a part of dimension B, then you have to make a pattern of dimension A. The pattern size will be larger than the final product. Second one is the draft allowance. Draft allowance is a angular allowance. Okay, to visualize this, if you consider the first one, you put the pattern into the mold, and these are the sands around it. You pack the sands properly, and then if you want to remove the pattern, you pull it upward. Okay, when you pull it upward, it will be always in contact with the sides. Okay, it will be always in contact with on all four sides, okay, of the pattern. But if you give a little bit allowance, that means an angular allowance, you increase the dimension of the pattern a little bit here, or you can consider the angle 1 degree or 2 degree. Okay, then that is called the draft allowance. If you do that, the benefit is that when you try to remove the pattern, because we need to remove the pattern to create the cavity, right? And if you want to create the cavity, then you have to remove the pattern.
Yes, sir.
And to remove the pattern, if you use like this on the vertical edges, the pattern will always be in contact with the sand, and there is a possibility of breakage on the sides. Okay,
Friction occurs.
yep, the friction occurs, as well as there is a possibility of breakage, breaking the edges. But when you allow the draft allowance, then if you lift it a little bit, then all sides gets disconnected.
And from there, yes,
Then
sir.
it will be much easier to remove the pattern, and it will not harm the cavity.
Okay. Yeah.
Okay, so the next one, the first one is the exterior allowance. This is the exterior allowance if you increase the dimension on the exterior side. But what happens when the sand is inside? Okay, if the sand is, there is a hollow shape, and sand is in this region, then in the outer side you provided the exterior draft. In here you provided the exterior draft. This is an enlarged view. Okay, this draft is not that much. Okay, it's very small, like 1 degree. Okay, or sometimes it can be less than 1 degree. Okay, and in the case of interior draft, you need to reduce the dimension of the internal dia or internal cavity, whatever it is. Then sand will be in here, and if you don't provide this allowance in here, then the sand will be always in contact with the surface, and a little shaking of your hand will result the breakage of this of the sands in this location. Okay, and that is why you need to provide interior draft allowance for the removal of the pattern to make the pattern removal easier. And not only in the case of sand molding, but also in the other molding too, you need to provide the draft allowance for the removal of the final product. Not only for the sand casting, you remove the final product by breaking the sands, but in the case of if you want to make the die casting, you have a metallic die and you want to remove the final product, then you need to provide the draft. Otherwise, for the to if you want to remove the final product, then it might break down. Okay, and that is why the draft is very important in the case of any sort of casting. Okay, any question?
Sir, I am not clear this part, sir.
You are not clear in this part?
Yes, sir.
And okay, let me clear it out. So you understand the pattern, right?
Yes, sir.
Okay, the, for to produce the cavity, okay, you put the pattern into the drag, right?
Yes,
Drag or cope or flask, whatever it is, you put the pattern in there and then you pack with the sand. You pack
yes,
with the sand, or the whole flask is packed with the sand,
yes, sir.
and sand will also be in this region, because in this region there is no pattern.
Yes, sir. There's no
Okay, sand will be in here, and let's consider that there is no pattern in here too. The sand is also in here. Okay,
okay. Yes, sir.
in that case, if you want to remove the pattern upward, okay, then the pattern will be always in contact with the sand,
10.
and due to the friction or a little bit of movement of the pattern, then the sand pile that is created in here, it might break.
Break. Yes.
Okay, and sometimes there is a possibility that with the pattern the a fraction of sand is getting out with the pattern because of the friction.
Friction. Yes.
Okay,
Yes, sir.
and to avoid that, if you uh, for the internally, if you provide a draft allowance on the pattern in here, okay,
Yes, sir.
then with the removal it will be immediately disengaged from the sand in here. Okay,
Yes. Yes,
and
sir.
that is why you need to provide the internal draft allowance if there is a cavity in the pattern.
Yes, sir. Understand.
All right,
Yes, sir.
and the third one is finishing allowance. If you need to finish a casting, then you need to provide you need to increase the size of the pattern. Okay, for the first two allowances we are increasing the size of the pattern, and this third one we are also increasing the size of the pattern. For average sized casting, allowance is 3 millimeter for ferrous material, that means the material which have iron, mostly iron, and 1.5 millimeter for non-ferrous material, for example copper, aluminum, or other non-ferrous materials. You need to increase the size of the pattern by uh, 3 millimeter or 1.5 millimeter to provide allowance for finishing. Once the final product is produced, and then you remove that 3 millimeter for the sake of finishing, and
Finish.
that is why you need to increase the size of the pattern. And number 4 is shaking allowance. The shaking allowance is that when you pack with the sand, okay, when you pack with the sand gets stick to the surface of the pattern.
Yes.
Am I right?
Yes, sir. Obviously.
The sand gets stick, and you need to release the pattern from the sand. And how do you do that? You use a hammer to lightly strike on this surface,
Yes.
on the surface, so
Surface.
that the pattern can
Break.
be disengaged from the mold,
Fold. Yes.
detached. It will not be completely detached, but there will be a little bit of energy loss. Okay, and that is why it will be slightly disconnected from the mold.
Mm.
And also, using a screw in here, you need to provide a screw in here, and you need to have that provision in the pattern so that you can fix the screw in here, and then you apply the force in this way and that way to get the other two sides released from the packing of the sand.
Mm.
And if you do that, there might be an increase of of dimension, right?
Hmm.
The cavity dimension will increase. Okay. And
Dimension.
if the cavity dimension increases because of the shaking, uh, then you need to reduce the pattern of that size. Let's say it is 1 millimeter on the east side, 1 millimeter dimension has been increased for the cavity. Then you need to reduce 1 millimeter for the manufacturing of pattern. And to summary this, all four allowances, let's say you have a final casting size of this size, and you want to produce the pattern for this. Okay. And then for to produce the pattern, you need to increase. I'll show only one direction. Okay. uh, you, due to the shrinkage allowance, you increase the size of the pattern, let's say this much. Okay. And for the draft allowance, you increase the angular dimension, let's say a little bit. Okay. That is for the draft allowance. And for finishing allowance, you increase the size a little bit, 3 millimeter for ferrous material, you increase the size of the pattern. And for shaking allowance, 1 millimeter, in this case you need to decrease the size. Okay. That means if you want to provide the finishing allowance 3 millimeter, then instead of 3 millimeter you provide a little bit less, that means 2 millimeter, because 1 millimeter is gone for shaking allowance. Okay.
Yes.
That is why we say that shaking allowance is a negative allowance. All other cases, the dimension of the pattern increases, but in the case of shaking allowance, the dimension of the pattern decreases. That is why we call it negative
Negative.
allowance. Okay.
Yes, sir.
And there is a final one that is called distortion allowance. When you want to manufacture the thin parts using casting, what happens is that if you produce a mold like this, cavity like this, after solidification, material has a tendency, because of the residual stress during solidification, the final product, when you take it out from the mold, will be expanded on this side. You will not get exactly vertical edges for the thin castings. Okay. If the thickness of this is very small, like 3 millimeter, 4 millimeter, or 5 millimeter, up to that. Okay. In that case, let's say this one is the expansion is 1 millimeter. 1 millimeter distortion occurs. Then if you want to make the pattern to produce a perfect U shape using the thin material, thin product, then you need to allow this distortion on this side. That means your pattern has to be inclined in the inside direction, so that after solidification, when you take out the material, this becomes perfectly vertical. Did you understand this?
Sir.
Sir, if you explain again, it will be
Sure.
much easier.
Okay. So your purpose is to manufacture a product like this, perfect U shape. Okay.
Okay, sir.
And you have manufactured the pattern same way, exactly perfect U shape pattern has been manufactured. You produce a cavity exactly U shape.
Okay, sir.
You pour molten material, you complete the casting, and then when you take the casting out, what happens is that the edges does not stay vertical because of the residual stress in the material. Okay, this edges gets distorted like this. You don't get the final product with perfect U shape, that means the vertical edges,
Yes, sir.
you don't get that. And to avoid this problem, you have to make the pattern like this, so that after solidification this edges gets distorted and gets perfect vertical U shape.
So how is the problem when you use the draft allowance in this part?
Oh, the draft allowance is not related to this. Draft allowance is different from this. This one is for the thin. That's why I left it for at the end, because draft is related to the removal of pattern, and this one is related to the final casting shape.
Okay, okay, sir.
Okay,
Okay, sir.
for the final casting shape you need to have like this. You need to do provide that distortion allowance. Okay, it is not related to the previous four. Okay.
Okay, sir.
All right, next we are going to talk about core. Since you have already seen the core, you have already seen the core in your first lecture. Oops, where is the video? Yep, there it is. I would like to show you a video for how core is manufactured and the purpose of core. Okay, and you'll be able to understand, and then later I will discuss about this. Okay, just okay. This is it. So if I go step by step here, okay. First, you need a mold. Okay, you need a mold of the shape of the core. You want to produce the core in here like a angular bend. Okay, and you need to have the similar size die manufactured using metal or anything else, or wood, anything else. You use that, and then you pour the molten material, sorry, not the molten material, the mixture of resin and sand into that cavity. Okay, the shape of the cavity will be same as the shape of the core, and in that case the core sands are mixed with resin. Resin is kind of binder. Okay, you mix sand with resin and then pour into the cavity, and after that you allow heat to cure the resin. To cure the resin you need to allow apply heat. Once it's heated, the resin is cured, then you take out the core. So this is the whole core in here. And how do you use the core? To use the core, you put the core into the cavity so that the molten material does not go into into those places where the core is placed. Okay, and the material will flow around the core. Okay, and that's what happens in here. So when you apply the molten material into the cavity, the material flows around the core, but it does not go into the core. And once the casting is complete, then you take out the casting, and then you break the core out. Okay, you just use the vibration to remove the core, it will break easily, and then you get the final product where there will be a hollow bend inside.
Yes,
Okay,
sir.
that is how the core works. And to go to the formal definition, is a core is a determined or predefined shaped mass of dry sand which is made separately from the mold. We don't make the core into the mold, we make the core separately using a casting method and then use that core into the mold to get the cavity into the final product. Okay, what are the purposes? The purposes is to obtain the desired cavities which otherwise could not be obtained by normal molding. That means if you look at the casting that we have seen in the animation, if you want to make the hollow uh, bent pipes, then there is no other way in the cavity, so that you can remove the material, remove the molten, you can restrict the molten material to flow into that region, and core serves that purpose. Okay, and in the pit molding it's a special kind of molding which is made on the floor, and the entire mold is made of cores. Okay, so all various types of cores are placed in a hole. Okay, for example, if I want to show you a little bit of the demonstration of that, in the ground, let's say this in the ground you have a cavity like this. Okay, you have a cavity like this, you make this is a ground. Okay, you make a cavity and then you insert uh, different types of cores in here, like whatever you want the structure to be. Okay, different types of core material are placed in here, and then if you put the molten material in here, then after solidification you remove all these cores and then you will get the desired outcome in here. Okay, these are the this is called pit molding. In this case, entire mold is made of cores. Okay, just you create a cavity and we place various types of cores in position and then you pour the molten material. Okay, that is the pit molding. Okay, and what is the function of the core in here? You don't allow the molten material to get into those regions where you don't want the molten material to go. Okay, and the third one is that to reduce the metal erosion in gates, runners, and pouring basins. This is also important. You have a cavity, for example, you have a cavity in here. Let's say this is a cavity, and this is the mold or flask. Okay, and you have a pouring basin in here, and there is runner and gate in here, and there is riser. Okay, there's riser in here, then you pour the molten material through this. Okay, and all these things are sand around it. Instead of using sand, you can use cores in these positions. If you use core, then you can use cores in here. Okay, if you use core, the benefit is that when you pour the molten material into the cavity, then there is no chance that the sands get eroded. Okay, sometimes when you pour the molten material through the sprue, then the surface sands get stick to the material, molten material. If the mold is not prepared properly, then surface sand get mixed with the metal, and that is an impurity when the sand gets mixed into the metal. Okay, and to avoid that, you can use cores in here, so that the molten material flows easily and there is no chance of contamination of sand into the molten material. And also you can use the core in the case of riser too, and that is not actually necessary to use in the riser. That is why it's not saying that gates, runners, and pouring basins. Okay, all these things can be made of core. Any question?
No, sir. No, sir.
Okay, and in addition, I can say that when we studied the scent molding, we said that we need to have a sprue pin placed in this position, right? And a riser pin placed in this position. And instead of sprue pin, you just use the core. Okay, and in that case, you don't need to remove that. it will be in that place, and you can pour molten material into the cavity through that. Classification, there are two types of cores according to the sand used, green sand and dry sand. We'll talk about the green sand and dry sand later. And according to the position or use, it can be horizontal, vertical, balanced, and drop core. To demonstrate that, if the core is placed horizontally, okay, then that is called horizontal core. If it is placed vertically, this is the core, then it is called vertical core. Okay, and if it is placed like half into the cavity, half into the half of a certain portion of the core is into the cavity, and certain portion is placed into the mold so that you can hold it. Okay, this is one sided, not the entire cavity is not covering. So in that case, it is called balanced core. Okay, in the case of balanced core, you need to sometimes add the chaplets in here so that it does not move up and down. Okay, and drop core, what is the drop core? Drop core, for example, you want to make a casting with a hole in here. Okay, with a
Yes, sir.
hole in here. Okay, go ahead. Hey, did you ask any question?
No, sir.
Okay, all right. So you want to make a casting like this. Okay, like this, and you want a cavity in the casting like this. So in that case, instead of using this kind of core, balanced core, okay, you can obtain that using the balanced core. Okay, you can get that using the balanced core placed in this position. But instead of using balanced core, drop core placement is much easier. Okay, and that is why if you want to want the cavity in there, then you prepare the pattern like this with the extension. Okay, with an extension to that. Okay, that means this one will be aligned in here. Okay, and with an extension in here, and using that extension, you put the core just from the top. From the top, you drop the core into position, and then you place the cope, and then you pour the molten material. Then material will not flow into that place. Okay, the same purpose can be served with the drop core. It is said we can call it drop core because we are just dropping the core into the cavity from the top. Okay, did you understand it?
Sir, I'm not. Yes, I'm
Not sure.
yes, sir.
Okay, actually this is a 3D representation would be much better.
Yes,
Okay, next time I will try to draw something three-dimensional. Okay, for example, if you just consider the 2D thing, okay, don't consider the 3D.
yes, sir.
Okay, you want to produce a part and there is no metal in this position. That means only the hash region is consist of metals.
Metals,
Okay,
yes, sir.
and there is no metal should go into that region.
Is in the cavity.
Okay, and
Yes.
that is why you need to make a pattern for this product, right?
Okay, sir.
And in the pattern, if you use this hole,
Mhm.
then what would happen? Sand will go into that region,
Yes, sir. Obviously.
and then when you remove the pattern, what will happen? You take the sand with the pattern,
Pattern. Yes.
and that is the disadvantage. If you take the sand with the pattern, then metal will go into that place.
No.
Okay,
Yes.
and how do you avoid that? Then you need to make the pattern with no hole in that region. Okay,
Oh, okay.
you need to make the pattern with no hole in that region, and that means there is no hole in that region in the pattern, and also you want to place a drop core in that position. That is why to place a drop core, you need to also add extra material into the pattern in here. Okay,
Okay, sir.
and after that you get the cavity. What would be the cavity size? The cavity will be the red line,
Mm.
right?
Yes, sir.
Cavity will be the red line. Then you don't want the material to be in this region, do you?
Yeah.
Because your final casting size is up to here,
Up to here.
up
Yes.
to here.
Yes.
Then in this region you place a core. This is the hashed region is the core.
Core.
And how do you place that core? This is the whole cavity. You just drop the core from the top
Okay,
in
sir.
that position, and then you pour the molten material. The material will not go in that place, and your final casting will be like this.
Okay, sir.
Did you get it?
Yes, sir.
Okay. And the properties of good core. What are the properties a good core should have? First one is the permeability. A core should have the permeability. What is permeability? Anyone can say what is permeability? Something should pass through something. Okay,
Yes,
that is
sir.
permeability. If you are during this COVID-19 era, you are using mask. Why?
Because the virus cannot
Yes, you
absorb.
don't want the virus or dust to penetrate through the mask and go into your lungs. But what do you need? You need air to breathe, right?
Yes, sir.
Air should penetrate,
Great.
but the virus or other dust should not penetrate through the mask. And the permeability is that the passing ability of the gas through what? Through cores. Gas should be able to pass through core. And why do we need that? Why? What gas should pass through the core? Because we're using molten metal, right?
Yes, sir.
And the molten metal actually produces gas. Different kinds of gas produced on the molten metal. Not only that, not only in the molten metal, as it is not exactly right. The molten metal actually does not produce any gas. The gas is produced because of the environment. The environmental oxygen, or sorry, environmental moisture actually evaporates when it comes in contact with the high temperature molten material, and that because of that evaporation, the gas, that means water molecules, when gets evaporated, that should pass through the sand as well as through the core. Okay,
Okay, sir.
that is the permeability. So a core should have the permeability. Why it should have permeability? Because when molten metal comes in contact with let's say I have a casting in here and a core is placed in here, the core is placed in here, and molten metal is around the core. Okay, and when molten metal comes into contact with the sands around it, there will be sand around in the flask. Okay,
Yes, sir.
then gas will be produced all over the area.
All right.
Okay, and that gas should pass through the core also, and gas should also pass through the sand. Okay, that is the permeability. So core should have permeability. Otherwise, if the gases are trapped in these regions, okay, then that will act as an impurity or defective casting.
Defective bubble.
You will get the defective casting because of the gas entrapment. So gas should pass through the core, and not only the not only the molding sand produces gas, but the core also produces gas because of the limitation of the binder or whatever you are using with the sand to produce the core. Okay, and the permeability should be there in the core so that gas can easily pass through the core. Number two is gas generation. Core should not generate huge amount of gas, because when the core is subjected to high temperature molten material, in contact with the high temperature molten material, the core should not produce huge amount of gas. If it produces huge amount of gas and metal gas gets solidified at the same time, the gas will be trapped on these regions. Okay, and then you will not get a proper casting. So core should not generate huge amount of gas, as low as possible. Number three is collapsibility. You produced a core, you manufactured the part, but core does not collapse. That means core does not get separated from molten material. It reacts with, it gets attached with the molten material. Then what will happen? You will not get the proper cavity. You take out the core by breaking, but the core surface will be attached with the molten material. So core should not behave like that. That means core should be easily detachable from the metal. When metal solidifies, core should not stick to the material. That is collapsibility. 4 is the thermal stability. As we use high temperature molten material into the cavity and the core is in contact with the high temperature molten material, so if the core breaks down at high temperature, then it will not serve the purpose. So the core should have high thermal stability so that it does not break, or it does not bend, or it does not react with the molten material, or at high temperature it should not break down, and that is called the thermal stability. Strength, it should have sufficient strength, because when metal contracts, then there will be a stress mismatch. Okay, and that is why there will be force exerted on the core, and it should not break. And at the same time, when you pour the molten material into the cavity, then because of the flotation of highly viscous molten material, at the beginning core will be subjected to the force on the upward direction. When the molten material comes at the bottom of the core, the course will experience a bending force in here, and because of that force, core might break down in this region. Okay, and if that occurs, then it is not good. Okay, core might break down in this region, and that should not occur, and that's why core should have sufficient strength to withstand the force exerted by the molten material from the bottom side due to the flotation, and as well as during the contraction, core should not break down. Okay, so these 5 are the basic characteristic, and there will be another one which is chemically stable, that means chemically inert. Chemically inert, that means core material should not react with the molten metal. If it reacts, then the surface, there will be surface roughness around the core. Okay, any question?
No, sir.
All right. So the next is the molding sand. Okay, so the molding sand, in the case of molding sand, the principal constituents of the molding sand that we use in the sand casting for the packing. Okay, for the packing of the pattern, and then to produce the cavity, we use the molding sand. And that sand, the principal constituents are the silica, that means silicon dioxide, aluminum oxide, 4 to 8%. Silica is mostly 86 to 90%, and there are some iron oxide and some smaller amount of other materials or alkaline compounds present in the molding sand. According to the nature, molding sand can be classified into 2 groups. One is natural sand, that means the sand that we take out from the river, lake, okay, by dredging. Okay, we get the natural sand, and the synthetic sand is that artificial sand. Okay, you manufacture the sand by mixing clay-free sand, binder, and other materials as required properties can be controlled easily. That means it is also the river sand, but you process it to make it clay free, but river sand contains certain amount of clay into them, and you wash it properly to get the actual clay free sand, and then you use binder. Okay, you use binder with that sand. The binder means the glue or adhesive. You use that adhesive with the sand to make the mold. Or for example, if you look at the manufacturing process of the core, you say you mix sand, dry sand or clay free sand with the resin binder. Okay, and that those sands are called the synthetic sand. You can control a lot of properties. You can control the clay content, you can control the moisture content, okay, and you can control the binder content and how much strength it will give you. All these things you can control, and that is called the synthetic sand. And according to use, the sand is classified as, first one is green sand. Green sand actually contains 18 to 30% clay and 6 to 8% water with the sand particles. Okay, and dry sand, no moisture. When you dry up the green sand, that is called dry sand. Okay, and there will be no moisture in the dry sand. And the loam sand, loam sand is 50% clay and 18 to 20% water. That means there is huge amount of clay. The loam sand is basically kind of when you make the brick, okay. When you make the brick, it has those contain sand, as well as there will be there will be a huge amount of clay, so that you can give it any shape you want. Okay, and the facing sand is the finely divided sand. Just hang on a second. All right, the facing sands is the finely divided bituminous coal. This is the coal product. Okay, when you in the coal industry, there is finely divided coals are present, and these sands are basically used into the cavity to produce better surface finish. Once cavity is prepared, you sprinkle the this bituminous coal or facing sand on the surface of the cavity, and then you use the pattern to finish it up. That means you use the pattern to make the inside surface of the cavity plain, and then you will get better surface finish. Okay, the dry finally, that means very small particular sand with bituminous coal, 2 to 8% bituminous coal given with that. Backing sand, actually the used sand, you cannot use the sand again and again and again. Okay, at some point the sands actually lose their various properties, and those sands, the used sands, are stored in a different place, and then you use for the used sand for different purposes. Okay, and those are called backing sand. And why does it called backing sand? When you produce a cavity, a mold, if it is a pattern and this is the drag, okay, if this is the drag and this is the pattern, the certain up to certain level you use the pure green sand in this region, and then backing sand is used on top of it to fill up the extra cavity. Okay, extra region of the drag, use the backing sand. Then the parting sand is actually used between the drag and cope. Once the drag is complete, then you sprinkle the parting sand in this region, so that for the removal of pattern you need to separate the drag and cope. Okay, and that parting sand actually provides that feasibility, flexibility, so that the drag and cope can be separated easily. Because when you fill up the drag and when you fill up the cope with the same sand, then it will stick with each other. Then you cannot remove the separate the drag and cope. That is why you need to use the parting sand on the surface, so that it can be separated very easily. Parting sands are is generally the dry sands with no moisture. Okay, then core sand, for making core you use the sand that you use to produce the core. And the system sand is called machine. In the case of machine molding, you use the system sand. All the sands that are being used for the molding together is called the system sand, in the case of automatic sand molding techniques. Okay, any question here? Nope. And also similar to the core, we need to have certain properties of the molding sand. Like for example, the first one is the permeability. It is similar to the core, similar as I discussed in the core section. The molding sand should have sufficient amount of permeability, so that gas generated into the mold can get out of the mold very easily. Okay, and what does the permeability depends on? The size of the sand, shape of the sand. If the shape of the sand is round, then there will be more permeability. If the size of the sand is larger, then there will be more permeability. Size is smaller, more packing occurs, and the permeability will decrease. The moisture content, if the moisture is high, then the permeability will be less. If the moisture is low, permeability will increase, because water molecule will restrict the gas passing, okay, ability of the mold. And clay content also plays a vital role. If the clay content is higher, then the permeability will decrease. Binder content is higher, permeability will decrease. Then you have to actually optimize all these things so that you get proper permeability of a molding sand. There is some other there's a huge discussion on permeability actually, but we cannot cover all of them. Just remember that the size, shape, moisture, clay, binder, all these things play a very important role to control the permeability. Okay, that means the size of the sand, shape of the sand particles, moisture content, clay, and binder. All these things affect the permeability of a mold. Next one is the cohesiveness. That means sand should stick to uh, uh, each other, right? That is the cohesiveness. Am I right?
Yes, sir.
Yes, sir.
So it will also depend on the size. If the size is smaller, there is more cohesiveness. If the size is larger, cohesiveness is less. That means they don't stick with each other. Okay, and shape. If the shape is irregular, then they can stick to each other. But if the shape is round, then they don't stick with each other. For example, the broken, if you have marbles, like a pile of marbles, you cannot keep them together. They get released easily. But if you have broken marbles together with irregular shapes, then you can make them piles, right? You can organize them into a pile. So that's how the sand works. Okay, if the shape is round, then cohesiveness will decrease. The binder content, if the binder content is higher, cohesiveness is higher. If the binder is less, cohesiveness is less. If the moisture content is high, cohesiveness increases. If the moisture content is too high, then you cannot make actually mold. Okay, if moisture content is low, the cohesiveness will decrease. Adhesiveness plays an important role, because uh, you are using a flask which does not have any support on the from the top and bottom. The entire mold has to be stick to the flask. Okay, the mold has to stick to the flask. That means sand should stick to the metallic flask, and that is called the adhesiveness. The sand should properly stick to the surface of the material. Otherwise, if you raise the drag, all the sands will drop down. If you raise the cup from the ground, all the sands will go down. You don't want that. That is why you need adhesiveness. That means sand should stick to the uh, another material, or the on the flask. Plasticity is basically the flowability. For example, you want to you have a pattern placed on the drag, in here. You pour sand up to this level, and then you use a hammer or a rammer, okay, to ram. You apply force on the sand, create a cavity like this with the hammer, so for the packing, okay. And when you release the hammer, then sand actually goes back to that position again. Then can you do the packing? Did you understand it? Maybe not. Let's say you have a pile of sand here, okay. You want to pack it properly, okay. then you apply the hammering. Okay, when you use the hammering, the sand, once you apply the force with a hammer, then this region gets deflected like this, and it remains in that position. That is called plasticity. That means mold has plasticity. It should, after application of force, the mold should be packed properly. Or mold should deform. It should not have behave like elastic, like you apply the force, it gets deformed, and then it gets raised again. You remove the force, it gets released again. So that should, you should, the sand should have the plasticity, so that you can pack properly. And for example, if you put the sand in here, the sand will be around this, like this, and the sand will not penetrate in this position. If you hammer it in here, then sand will gradually, with the hammering, gradually fill up that empty space. But if the sand does not have plasticity, it will not happen. That means the empty regions will remain empty forever, so you will not be able to produce proper casting. Next is the refractoriness. That means sand should not withstand high temperature, because the molten material at high temperature, so sand should also withstand high temperature. It should not disintegrate or break uh, due to the exposure at high temperature. Okay, it should have refractoriness. That means the ability to withstand high temperature. Chemical resistivity, obviously sand should not react with the molten material. It should be resistant, chemically resistant, so that it does not react with the molten material. Binding property, it should have the proper binding property, so that the sand gets stick together, and also the adhesiveness can be obtained with the flask. Okay, and the flowability, the sand should flow to the integrated spaces. For example, you have a pattern like this. Okay, and the sand should penetrate all these regions. Okay, it should be have like not exactly liquid. You cannot make the sand liquid like nature, but it should have sufficient flowability, so that when you apply forces, the sand gets into all the small spaces of the pattern. Green strength, it should have sufficient strength, so that when you pour the molten material, it should not break down. When you raise the drag, it should not break down, so it should have sufficient strength. That's it for properties of molding sand. Do you have any question in here?
No, sir.
All right. So next is the sand testing. Okay, what sort of testing we should do? Firstly, permeability. The sand mold should have the proper permeability, so we need to test the size, shape, moisture content, clay, and binder. All this testing needs to be done. Otherwise, you cannot say that this have a sufficient amount of permeability. Grain fineness, if the sand particles, the particle size distribution, you should not use very large sand particles, and also you should not use all the particles very small size. So there should be a distribution that also being we need to test. And we need to test the strength, how much strength a molding sand should provide, and the moisture content, clay content, that's I already said, and the flowability. Those are the things that we need to test for the molding sand to periodically, so that we for example, you used a certain amount of sand for casting, like again and again and again repetitively, and then you'll not get proper casting. At some point, you'll not be able to manufacture the mold, and mold will break down very easily. So periodically sand test is done, and then ensure that the mold will be proper, and then the gas permeability will be proper. That is why you need to do all these things periodically. For example, you have got a new batch of sand from a new location, then you need to do all these tests to get to know the properties, and to know how much moisture you might need to add, how much binder you might need to add into the sand to manufacture the molding mold. Okay, so all for those purposes we need to do the sand testing. Okay, I think that's all for today. In the next lecture we'll start with the classification of casting process, and also the shell molding. I thought we might be able to cover this today, but it's not. Okay, so in the next lecture, we will be covering the classification of the casting processes with the explanation of shell molding process, and let's see how far we can go in the next class.